All right, let's learn how to make a decision using hypothesis testing and also learn how to visualize whether your sample t statistic lies in the rejection region for a one-tailed one sample t-test. We look at both the left-tailed and the right-tailed test. We'll also look at a two-tailed test. So in this screen that you see here, we see a right-tailed test where we see our test statistic in the dotted red line clearly in the rejection region. And so it gives us enough evidence to reject the null hypothesis. And I'll share with you how to write code that can do this visualization. And we will do the same for a left tail test. And we'll also do the same for a two tail test, which gives us a way for, in this case specifically, we cannot reject the null hypothesis because it's not in the rejection region. But I'll also show you how to run this code in such a way that if the test statistic falls in the rejection region, that we can actually visualize it. So two goals: look at various situations as to how you can make decisions using critical value or the cutoff value and using your sample t-test statistic. And second, we will learn how to calculate and make a decision using the p-value. Yeah, so those two things. And third, finally, we will learn how to visualize all of this so that it's presentable and we know how to draw these graphs using Matplotlib. So those are the three goals of this video. Let's go through step by step how to go about doing this. Yeah, so let's start at the very top. What you need is you need some starting code that you need Matplotlib. You need some libraries with NumPy and stats, which gives you an easy way to calculate percentiles and probability distributions. Now, assuming for all of these tests, I'm using a 5% alpha or 95% confidence interval, and I'm assuming that I have the fixed data set with 2,500 data points. So this is very important. You might have a different data set with a different number of items in it, so you'd want to make sure that you use the right value. Depending on the number of items in your data set, the degrees of freedom will change. So you'd want to calculate this every single time for different degrees of freedom if it changes. Yeah, I'm using a fixed example. You'd want to do this for the data that you're dealing with to get the output that you desire for your data set. So manually we would generate, let's say, random t values, about 1 million of them from the standard t distribution, and we will use this to actually draw this histogram. So we've just generated 1 million t values, and if you see, this will be in any order. It's not going to be sorted, but pretty much from the t distribution, standard t distribution, it'll randomly give us t values. Yeah, but if you get 1 million of them, you can actually, if you sort them, you'll get a really good shape of t values based on, if you draw the histogram, you'll get a really good shape of the density with which they occur. Yeah. Okay, so now that we've gotten these t values, what we want to do is set up an example of a right tail test with 5% alpha, 95% confidence interval. The thing you do on your own for your specific example is you calculate your sample t statistic. You calculate standard error, and you can then use that to eventually calculate your sample t statistic. Yeah. So I am using a fixed number just to illustrate, but you should calculate your t statistic. And we would have the critical value. This is again calculated based on like your confidence level, 5% alpha, 95% confidence interval. What you would do is you would look at all of these simulated values and maybe calculate the percentile as one way. If it's 95%, you can specify that here as 95th percentile, 95th percentage, and then that'll give you the critical value from the sorted list of 1 million t values, a value that you can use as the cutoff value. Yeah. So assuming you've done this, you've done the t value, t statistic, sample t statistic for your experiment that you ran, and you've calculated the critical value, the cutoff value for the alpha that you care about If your alpha is 1%, then this will change. But I'm using fixed values just so that I can illustrate how to make decisions, how to visualize, and then how to calculate the p-value and make decisions based on the sample t statistics and cutoff. Yeah. So assuming you've done this for your test, and you would first calculate the p-value. So for a right tail test, what you would want to do is you would want to look at all of your simulated values and see which of these are more extreme than the critical value that you care about. In this case, 5% is your alpha. So you look at, sum up all of those values that are more extreme than the critical value that you have. In this case, 1.64. So once you sum them all up, the proportion of all of those items from a million t values will give you the probability or the proportion of how rare is your sample t statistic, and that'll give you the probability. So that's your p-value, the probability of how rare is your sample t statistic. In this case, it tells, I've just calculated this, you'd want to do this for your own. I've calculated this to be 1%. Yeah, so this is significant. Yeah, because our alpha is 5%, p-value is significantly lower than the cutoff that we have of 5%. So this this sample t statistic would be significant for us. Yeah. So this is the foundation needed. You would want to figure out how many items you have, n, the degrees of freedom. You calculate simulated t values. You calculate your sample t statistic. You would calculate the critical value for the alpha that you care about. And then you would use that to calculate the p-value, which is the proportion of all values more extreme than the critical value that you care about. Yeah. Having done this, you can make decisions. If you're interested in knowing how to do each of these steps in more detail, send me a comment so that I know that this is not clear, but I'm hoping all of this parts are clear. And now what we are interested in learning is how to make decision. Now that we have our t statistic, we have the p-value, we have the critical value, let's make a decision whether we can accept or reject. We have enough evidence to reject the null hypothesis or not. Yeah. So for a right tail test, we're looking at right tail test. We can make a decision by comparing the t statistic if it's greater than the critical value. Yeah. Right tail test, t statistics falls inside the critical value. Then we have enough evidence to reject the null hypothesis. Yeah. If not, we don't. So this is one way. Using the sample t statistic and the critical value, you can make a decision for a right tail test. You can also do that same thing for p-value, using p-value. So you've calculated p-value based on how rare your sample t statistic is. So this is an optional way, but a much easier way to communicate the results using p-value. So p-value less than alpha is also a way to say we have enough evidence to reject the null hypothesis. Yeah. So these are two ways. Both will give you the same result. Either one, pick one, and then consistently just use it, and that gives you the result. So you can make a decision whether there's enough evidence to reject the null hypothesis or not. And you can visualize this as well. So let's look at the code of how to visualize this. You would visualize using all of the million simulated t values with a histogram. Say, hey, I want 100 bins. I want it to be a density plot. Yeah, so that I can find out at what proportion each of these values occur in those bins. And then I have these bins to be having an edge with a color black. So mark those bins with black color. So this, you see these black lines, that's what this is. It'll draw this histogram, and I want this histogram to be in blue. So I'm specifying the color of the histogram, and I'm giving it all of the configuration needed to draw my histogram. So what that line of code does is draws this histogram, this blue line. Yeah. This blue histogram with all of these edges with black borders and blue shade inside. So we've still not drawn this green dotted line, which is our cutoff or the critical value. We've not drawn the sample t statistic, the black dashed line. And we've also not drawn this green shaded area, which is the rejection region. Yeah. So let's, and we've not drawn the legends, we've not given the title, none of that. So let's figure out how to do that. So once you've drawn this blue histogram, what we want to draw is this red dashed line, which is going to represent where does our sample t statistic lie. Yeah. So we would do a plot.axv line give it the t-statistic value. So that'll draw this dotted red line, and you give it the color, it's red that you want, and it's a dashed line, and you'll give it as part of the label, you would give it the value so that it starts to show up here, yeah, 2.29. So that draws that red line. This code will draw the red line. Similarly, we want to draw the green line, the cutoff value. So we'll specify the cutoff value, the critical value. We will mark this as a dashed green line, and we'll tell it where to draw it. So it's at this place we would want to draw it. So that draws this green dashed line. And then now we want to shade this entire area, starting the critical value till the very right edge of this graph with green. So this color will fill that with green. So it'll fill that with green color. And so then that'll make this rectangle show up with green color. You can also do this with this one line, but I've just given you what each of these line does as comments. So you can go through that. We add an X label, Y label, title, legend, and then we make the we will make the graph show. If we don't add this semicolon, colon, yeah, so then it will actually it'll print out all of these values. So you just add colon here, yeah. So then that'll get rid of all of those arrays that are being printed, yeah. So now, see, we can easily see where our test statistic lies, yeah. In this case, our test statistic is way outside the rejection region, so we cannot reject the null hypothesis, yeah. But if I were to rerun this code, and this is using an older value from below, that's why the test statistic is here. But if I were to rerun this code from the top and using this test statistic, which is 2.29, which is, somewhere here, then it will draw it more accurately. So there's enough evidence to reject, and then let's draw this again, and we will see that it goes and draws it correctly. So this is one way in which we've drawn this right tail test in a way that the test statistic is clearly falling in the rejection region. We've also learned how to make a decision based on p-value, how to calculate the p-value, and also make a decision based on the critical value and the sample test statistic. So that's the basic, the first part. Now let's look at doing the same for a left tail test. Yeah, same alpha. The key difference is that now you would count all simulated value less than equal to the critical value, because on the left hand side of the critical value, that's the main difference. And then the decision part would also be if the t statistic is less than the critical value, then you would have enough evidence to reject the null hypothesis. If p-value is less than alpha, then you can have enough decision making power as well, yeah. So same setup, except that some of this direction changes based on whether it's a left-tailed or a right-tailed test. And so when you rerun this, you would see that both will give you the same result. And if you rerun this code, it'll tell you that on a left-tailed test, the sample test statistic clearly lies in the rejection region, and you can draw this. The key difference here, folks, is if you want to shade the left green triangle instead of the right green triangle, you'd want to start at 0, which is the left edge of the plot, and plot all the way to the critical value for the left tail test. For the right tail test, you would start at the critical value and end at the right edge of the plot. So that gives you the plot on the right hand side. Yeah. So that's the only main difference. You can see all of this code in the comment as well. So you will see the link to this code that you can use. Now let's look at how to do this for two-tail tests. Yeah, so two-tail tests with 5% alpha, 95% confidence. What we would need is a cutoff at 2.5% and at the lower bound, and the cutoff at 97.5% on the right hand side, because there's 5% of this area that is in the rejection region. So 2.5% on the left, 2.5% on the right. So we would use those percentile numbers, 2.5% and 97.5%. Yeah. So let's say our sample t statistic is minus 2.29. Yeah. So the difference here, folks, is you would want to look at alpha by 2, because 5%, half of 5% on the left side would be gone. That's the percentile, 2.5%, and 1 minus alpha by 2. So this is 97.5%. So you get a different value for lower critical cutoff or lower critical value, and upper critical value or the upper critical cutoff. You get different values for that. And the p-value is also going to be calculated differently. Remember, p-value is calculated as extreme values greater than the cutoffs. So one way is to look at all values, count all values lower than the left cutoff and higher than the right cutoff, sum both of them up, and look at that as a proportion of total values or simulated values. Or you can just look at the absolute values of the simulated values and count all of them that are greater than the absolute value of the sample t statistic. That's also one way. It's the same setup. It's going to count both of them and then look at that as a proportion. So that's the key distinction to remember, which is how you calculate the p-value. As long as the concept, you use it consistently across left tail, right tail, and two tail, then you should be fine. Yeah. So there are two ways. I've listed both of them down here. Count all values lower than the critical cutoff plus all values higher than the upper critical cutoff, or just use the absolute values for all the t values and count them. And that's also one way to find out the p-value or the proportion or the probability of seeing a sample test statistic as rare as this one, which is minus 2.29. Yeah. Now, again, if you want to make a decision, you would want to look at the absolute value to make a decision. Yeah, because, or you use the right signs. If you're comparing if your sample test is negative, then compare it with the negative value of the lower cutoff. If it's positive, compare the upper value of the upper cutoff. And similarly, p-values again remains the same as long as you used the right way to count all the values as I have highlighted here. Yeah. So you get the same result. If you simulate, the key thing here is now we'll have to need two different rectangles in the rejection regions, one on the left and one on the right. So we'll combine both the right tail and left tail. We'll start at 0 and go to the lower critical value. We'll start at upper critical value and go to the right edge of the graph. So right edge is denoted by this 1 passing in the 1 parameter, and the low edge is passed by 0. Yeah. So everything else remains the same, except that now you would need one more. So you need one more critical value dashed line. So we'll have two green lines, remember? So we would not only have the lower cutoff, but also the higher cutoff. And so if your test statistic is in this area, then you cannot reject. You do not have enough evidence to reject the null. But if it falls inside, then you have enough evidence to reject the null. If I rerun this, you will see that this graph will change. And now it falls within the cutoff region. Before I showed you an example where it didn't fall in the cutoff region. So that's the code of how you visualize this, how you make decisions based on these two. And you can do that for various combinations now within cutoff, not in the cutoff region, in the cutoff region, how you make decisions. And you can be using this pretty much everywhere. This one sample t-test is very powerful in that sense. Yeah. Good luck.